So good morning, everyone. Uh, Again, the plan for today is I'm going to basically go through Moodle and just make sure that we're all on the same page. I do want to clarify a couple main points of emphasis for the levers and the pulleys. Um, and again, make sure everybody's questions are answered going into our first exam next week. So, just like I said in the chat, if anybody has any questions at any time about anything while I'm just kind of doing these kind of summaries, feel free to ask. So, I think what would be best is if you pulled up your Moodle, if possible, and because I'm literally going to kind of summarize, where we're at, what we're talking about here. So, first thing I want to mention is that Sarah Stamey, my internship student, is going to be at the computer lab from 10 to 12 today and on Friday. If anybody has any questions or wants some practice or clarifications or insight. So that's today, Wednesday, the 18th, and Friday, the 20th. Okay. All right. What I'm going to start off with is I'm going to clarify what you're going to need to know for levers and pulleys. So again, levers and pulleys can get very confusing. I'm trying to just stick to the points of emphasis for all things biomechanics in this class, because again, we have 3 months, and I'm just trying to introduce you to certain things that you might see in the future where you could develop and advance it. So we're sticking to the basics here conceptually. All of the different things that I've kind of been introducing you have pros and cons, right? Trade-offs. Mobility in the shoulder is a trade-off for less lack of stability in the shoulder. You get more injuries up here because you have more motion. Hips, you have less mobility, but you have greater stability. So the trade-offs, right? So we talked about trade-offs in movement strategies. Simultaneous movement has more accuracy and more force application on something because you have all these different muscle groups working at the same time. All hands on deck kind of thing, right? Sequence motion, one joint motion done at a time. Each joint, if you think about it, and all the muscles that influence that joint have to be able to handle those forces by themselves in a summation fashion. They can't work with other people. When it's their turn to work, to activate, to do their job, they have to be able to handle all of that load. So that's why you can't take something heavy like a shot put and throw it like you would a baseball, because my shoulder and my elbow can't handle that force. So sequence motion, maximum speed or speed of distal segments at the expense of force and accuracy. Trade-offs. Same thing with levers and pulleys. So if you think about we pushes and pulls are the two main types of forces, contact forces that we use. We push on things and we pull on things. And so if you pull up the on Moodle basic biomechanics of pulleys and levers, in class, I told you, look, guys, in engineering, you're going to learn all the different simple machines because they use those in everyday lives. But in our bodies, the key ones are levers and pulleys, and there's a lot of similarities. But I'm going to clarify the major differences. Okay, pulleys, like pulleys, it's going to be looking at how muscles pull and can have advantages of simple machines just by the pulling. And there's different classifications. I'm going to clarify the ones you're going to need to know. But it's a pull concept for trade-offs. It's a pull concept of advantage. Levers is more pushes and pulls, right? So you look at the first slide, you see the person using a lever to lift the heavy rock. We always use this analogy. I don't know how many times someone's actually had to use a lever to lift a heavy rock, but apparently it happens a lot in the cartoons. So yes, you're pulling, your muscles are pulling, but your hands are pushing on that other end of that rigid link of that lever, and thus the other end is pushing on the rock, right? So a lot of times when we look at leverage for levers, it's a rigid link like a bone, right? Bones are rigid, and we're looking at pulls and pushes. We pull on one end and we push on the other end. Whereas a pulley system is more traditionally pulls. It's just pulls, advantages and disadvantages of pulls. Okay. Going down for the important things. So look at the types of machines within the body that we're going to look at, levers and pulleys, all about what you need. So if you need a system that's going to help you balance, and I'm pretty much giving you what I'm going to ask on the test, classification of what you need is for what you need it for. So if you're trying to balance, like if you're trying to balance on one foot, one leg, you're trying to balance anything. When I mentioned that the key word is balance, we're looking first class systems. First class systems where you can have a teeter totter and you can have muscles on one end and the other end trying to work to maintain your center of mass over your base support. And that could be first class at the hip, the ankle, both legs, when you're trying to balance, muscles in the front and the back, outside, inside. You're trying to keep your eyes level. There's going to be muscles on each side of your vertebra trying to help keep your eyes level, balancing in the front and the back, trying to balance. Keyword is balance. Because first classes can do speed and can do, I'm not going to ask those kind of questions on the test because it does get really confusing. Balance or redirect of an applied force that I told in class. In other words, here's the lever, the rigid link, right? The bones. I pull down on one end, it makes the other end go up, right? And that's similar to pulley as well. But I'm going to talk about the class of pulley and now that's different. So what do you need it for? If you need muscle leverage that produces speed and range of motion, like you're trying to go real fast, like it's sequenced motion, you're going to need to optimize more third class leverage. Third classes are specifically for speed. And in previous class, I explained how that happens, right? That application is very close to the axis. So a small change of motion close to the axis produces a big sweeping change further away. So when you need speed, and remember, if you're going fast, you can't do it heavy. Those things are contraindicated. So third class arrangements of our muscles are very advantageous when we're trying to move our joints fast. Second class arrangements of muscles are advantageous when we're trying to move something heavy. In addition, when we're trying to slow down motion, when you're putting on the brake, that's a lot of force. So second class advantages are for moment of the muscles pulling farther away from the axis. And the trade-off is those contractions can't happen necessarily fast to create motion, specifically concentrically. They're running on the outside lane of the track. And when you have advantages that are on the inside lane, those outside lane muscles just can't contract fast enough. In class, I said, and this to me is a really good example. Usain Bolt can choose to jog, but I can't choose to sprint. So when you're doing something fast, only third class advantage types of muscles can sprint and keep up with what you need. But when you're doing something heavy, or when you're putting on the brake eccentrically of muscles, any class can help. Just think about it. If you're doing something really heavy, it's going to naturally go slow. So you want all hands on deck. You want even if the leverage of that muscle isn't advantageous for torque, it's contributing something. Does that make sense? So even when you're doing something real heavy, you want any type of muscle, any type of leverage possible, because it's naturally going to be going slow. So on the test, it's going to be, what do you need it for? Do you need to move a joint really fast? You're going to need thirds. What muscle leverage arrangements help with torque, force application through distance, right? Moment arm. seconds. Which ones are advantageous for balance? Firsts. That's kind of a so what, all right? And I give some examples, and I even link a little video, a short little YouTube video that I like on levers. All right, let's go to pulleys. Pulleys are very similar, except they're just looking at the muscle. It's not like the muscle pulling on the bone to create, it's just the pulley pull. It's just kind of looking at how muscles can have certain advantages in the body. There's 5 classes. Some of them are weird. Some of them are like in the eye, there's a little hook and it redirects the first class. Pulley is like the patella. I think everybody's very familiar with that. How the patella, that subclass sesamoid bone, increases the angle of pull of that muscle going into the tibial tuberosity, right? So they call it an external support. That's sesamoid bone. So this is page on the pulleys and levers. It's after the lever video, so pulleys. So you're going to need to know an example of first class. That's like the patella, where the word they use is an external support, gives an improved angle of pull. You see class 2 in the eye, don't care. That was part of the materials that I got at Auburn, but that's not really applicable for this class. Look at class number 3. This is just another way of looking at a patella. So it says the joint serves as the pulley, but if you think about it, look at how those condyles of the femur and the tibia shoot out. They jet out, or they protrude out is a better word. Tubercles, tuberosities, those are just fancy words for the bones kind of poking out to give you advantage, give you leverage advantage. And so if you look at the first class and that patella, how it jets out, and then you go to the third and you look at how those condyles jet out, it's very similar. So let's apply our basic trig. That muscle's kind of running down, even though it's kind of in quadrant 1, it's very, very steep. That basketball goal is almost vertical. But look at when it gets to the knee joint itself and those condyles, those condyles kind of force it to kind of change angle. And now the angle that's pulling on the tibia is much more, let's see, trying to think of a word, oblique. Try to think of a word y'all heard before. So it comes off that muscle comes off the pubis here, but after it gets redirected by the natural third class pulley of those condyles of the joint, it goes from pulling here to actually pulling there on the tibia. So in other words, much more vertical, and now much more combination of vertical and horizontal. Okay. The other class that I want you to know that comes in commonly is the 5th class. So know an example of first, patella, sesamoids. Thirds, the joint itself, the condyles, can help in a similar fashion. It's just not the sesamoid itself that's housed in the muscle. And then fifths. This is really cool. And if you notice, all of the 3 that I'm holding you accountable for have something in common. But instead of a bone serving as the leverage for the muscle, or bones of the joint itself serving as a leverage, a muscle serves as a leverage. So in the body, you have a ton of muscles that are deep, and then on top of them are superficial. Your soleus in your calf is deep, and your gastrocnemius is superficial. So the gastrocnemius sits on top of the soleus. And that muscle that's deep, or more on the inside, serves as the pulley for the muscle that's over the top. So in this example, they picture on the left, this is the last picture. And then again, I have a little video for you guys on pulleys. You see the biceps brachii crossing the elbow in the front. but underneath it is a muscle called the brachialis, and the bicep gets to piggyback on top of it. So again, instead of a bone serving as the leverage pulley, you literally have a muscle that another muscle can sit on top of to have a better angle of pull. Okay. So that's what you guys are going to need to know for the test about levers and pulleys. All right. Now, before we clarify the muscle stuff, I posted, even though you guys knew how to find all the lectures, I went ahead and posted them all on Moodle, make it easier to find. And reminder that a lot of the last part of this exam 1, muscles, is 310 related. What I mean by that is in 310, I taught you there's as many groups of muscles as there are joint motions. We need to have muscles that pull in every direction of motion to influence motion, right? So in other words, if our cervical vertebra has flexion, extension, sagittal, right lateral, left lateral, frontal, right transverse, left transverse, transverse, we have to have muscles that pull in a direction of flexion. We call those flexion pullers. This is where we go into what are those muscles. Why are they flexion pullers? Because we need to see how they pull in a direction of flexion. We're going to have extension pullers, right lateral bending pullers, left lateral bending pullers, right transverse pullers, left transverse pullers. I'm starting off, and for the whole rest of the class, we're going to go into all the major joints of the body and look at all the different major muscles of the body. The reason I start off with cervical, and I'm putting this in your first unit, is because we're simplifying it. There's only going to be 4 major muscles. And if you like, Dr. Campbell, there's 6 groups. How are there only 4 major muscles? Well, for this class. And that's because different muscles can partner with other muscles depending on the plane of pull. So in other words, I'm going to show you my right and left sternocleidomastoid are agonist sagittally. Their pull is the same in terms of flexion pull, so they're both flexors, but they're antagonistic pullers frontally. One is trying to pull right ear to right shoulder. The other is trying to pull left ear to left shoulder. When they work together, they can cancel out frontally and work together to pull sagittally. And just as an example, okay? So understanding how muscles pull is the most important part of this class. The practical applications of what do muscles do because you understand the direction of pull is really important. We identify who do we need, our agonist, because of why we need it. An external force is trying to make me bend to the left. I need muscles that are pulling to try to make me bend to the right. 310 stuff. All we're doing here is saying, all right, I identify that I need flexors, extensors, right laterals, left laterals. I'm going to stay away from transverse right now because it's hard to see in that dimension. Who are those muscles? Who are the flexion pullers when I need them? Who are the extension pullers when I need them? Who are the right laterals? Who are the left laterals? And that's where these lectures that I posted come into help. Okay. So a couple things. The PDFs are meant to complement the lectures, right? So notice you have PDFs, materials, and then you have lectures. What I want to emphasize right now is muscles, motion, and contraction, that PDF, that kind of, and I lecture on it. The lecture for Monday is that basically it's a 310 review. And then the major muscles of the cervical, that's today's lecture. And then what I love is this new thing that I just started this semester working with a former student. It's the PowerPoint. So if you look at the in between force couple example with the cervical and major muscles of the cervical, you'll see major muscles of the cervical power. If you click that and pull it up, I love how these little GIFs, these little videos, if you click play, the important thing on these videos isn't traction and figuring out. That's all stuff we got to figure out. Like I taught you in 310. What I love about these videos is it specifically just shows you how they pull. Okay. It shows you how they pull. So right lateral bending, pull the right sternocleidomastoid, for example. And again, you're going to watch this in the lecture videos, but this will just hopefully help make sense. We are limited in teaching and understanding with two-dimensional flat pictures of things. Right? So this clock is kind of in 2 dimensions. Right? There's up, down, there's left, right, but there's no depth. So a lot of times when we look at pictures of muscles, the muscles have 3 dimensions of pull, potentially. The muscles at your cervical vertebra are going to have 3 dimensions of pull. What does that mean? You're going to have one muscle that pulls sagittally, frontally, and transversely. And a lot of times it's tough to see all the 3 planes of pull with one 2-dimensional picture. So what I mean by that is if I showed you a picture of my right and left sternocleidomastoids, seeing the teeter-totter pull in the frontal plane is a heck of a lot easier than seeing them pull in the sagittal. Sagittal, we would kind of want more of this view to see the sagittal pull. And similarly, it's kind of hard to see the transverse pull of these motions in one dimension. So that's what I kind of like about these 3-dimensional real life, not real life, obviously it's not real life, but where you can see direction of pull in each dimension. So the first slides are lateral pulls. The next slide goes into the first slide is lateral and transverse. So it's going to show you here, and it's going to show you here. It's going to show you here, and it's going to show you here. And then the third slide shows you how they work together, pull forward, canceling out frontal, canceling out transverse. And so, and they have it for the erector spinae as well. So I really like this edition for visual learners, just to be able to see how they're pulling. You're going to hear this in my muscle lecture, but how to learn the specific muscles in the group comes down to different learning styles. Some of you will just memorize, and that's okay. But I also teach a tool with cross-sectional anatomy where we take a limitation of a 2-dimensional picture, but based off of how we look at it, we can see things 3-dimensionally. So the cross-section, our neck is somewhat circular, our wrist is somewhat circular, elbow is somewhat circular, everything in our body is somewhat circular. Mine's more oval. But when you look at things from a cross-section and you can see the bilateral axis, the anterior posterior axis, so like here's a cross-section. So this would be like a cross-section of my neck, circle of my neck, and I'm rotating it so that you can see it. That's all I'm doing. So like this would be the front, the back, the right side, and the left side. Okay. And what I teach you in the videos, or obviously when I'm not, I'll do it in class when I can, but in the past videos, the one for just this one, is that the function of a muscle is based off of how it crosses the joint. It's not about origin and insertion as much as it is how does it cross the joint. If the muscles cross the neck, the cervical in the front, they're going to be flexion pullers. And if they cross the neck in the back, they're going to be extension pullers. If they cross the neck on the right side, they're going to be right lateral bending pullers. And if they cross the neck on the left side, they're going to be left lateral. And that's all because they have torque, they have moment based off of how they cross. So the ones in the front, flexion pullers. Right side, right lateral bending pullers. Left side, left lateral bending pullers. Posterior, the back, extension pullers. The hardest one, but I'm telling you, you're going to get the hang of it, is the rotation pullers. And I have a separate little slide that shows what a force couple is. A force couple is a fancy word for something that's really common that we've experienced on the playground. If you're at a merry-go-round, right, and you want someone to rotate the merry-go-round and you want to go fast, the most efficient way to do it is to have one person, see, on one side of the merry-go-round. So here's the merry-go-round, here's the axis. You're going to do something like this, where you have one person on one end pulling this way, the other person on the other end pulling the exact opposite direction. But notice the linear is opposite, but the rotation was the same. They're both trying to spin the merry-go-round the same. The torque is the same. The linear force is opposite, but the torque influence is the same. And so that's how our neck muscles kind of work. When we want to rotate our head to the left, we have one muscle that's in the front right working with another muscle that's in the back left, and they can force couple, they can twist. Like, I guess like taking a basketball. If you want to spin the basketball as fast as you can, I'm going to probably have one hand on the front right side, another hand on the back left side, and I can use those two different linear forces to create the same rotational force. It's all in the lecture, so don't freak out, but I'm just giving you a heads up of kind of how all this stuff works. So now, instead of trying to memorize 6 different lists, so like who are my cervical flexors, right and left sternocleidomastoid? Who are my cervical extensors, left and right erector spinae? And I explained why we use a group within a group. There's just hundreds of little intrinsic muscles in there. You'll learn all those specific ones in grad school. Spinalis, iliocastalis, longissimus, all rotary. But if you learn lists, you'd get a lot of different muscles that are sometimes working with, and then sometimes they're not. Like sternocleidomastoids are agonists sagittally, they're antagonists frontally, and they're antagonists transversely. It gets confusing. So with one circle, it's like learning how every body meaning the muscles, sit in class is the analogy I give. So I'm going to use numbers here. 1, 2, 3, and 4. So let's say you have 4 muscles. You're going to just learn how they sit in class, the ones in front, the back. And when I need flexors, you know that the flexors are anterior, and that's muscles 1 and 2. When you need extensors, you know those muscles are posterior, so you need 3 and 4. When you need right lateral pullers, you know those are on the right side. You're going to need 2 and 4. And when you need left laterals, you're going to need 1 and 3. And then the last thing I teach you is the force couple. How these muscles, that's what these rotation arrows are for. How those muscles 2 and 3 can work together if you need left transverse pullers, if you need left transverse cervical rotators. This muscle working with that muscle can work together to spin you this way, pull that direction, that direction. Okay. So I will never, and I say this in the videos when you watch it, I'm never going to ask you to draw a cross-sectional class circle. And when I say class, like if you had to name as many students as you can in class, you're probably not going to see a list. You're going to see, well, who sits in front of me, who sits in the back of me, who sits on the left side of me. It's one visual that answers all the different questions. Okay. So on the test, I'm going to hand out blank sheets of paper. And when the test starts, you can more than welcome to write down cervical flexors or right and left sternocleidomastoid, my extensors or right and left erector spinae, my right laterals, my left laterals, my right transverse, my left transverse. It's fine. Remember, cervical, I'm only holding you accountable to 4 major muscles. When we get into the trunk, it's going to be more involved. Ankle, there's going to be more involved. Knee, there's going to be more involved. So the students that do the visual with the cross section, there's less to write, if that makes sense, because all of the answers are just there in the cross-sectional anatomy. So I hand out blank sheets of paper, the exam starts, and you just draw a circle, and you put right sternocleidomastoid in the front right quadrant, left sternocleidomastoid front left, right erector spinae back right, left erector spinae back left. You draw your rotation arrows, right sternocleidomastoids pulling in a direction of left transverse, left erector spinae, left transverse. You do what I teach you how to do, and you draw that, and then all your questions are answered. What are the functions of the right sternocleidomastoid? You could literally just visualize it. You don't have to draw it, just visualize it. It's a cervical flexor, right lateral bender, and a left transverse rotator, because that's how it pulls. What are the functions of the left erector spinae? It's an extensor, left lateral bender, and left transverse rotator, because that's how it pulls. So, and then on top of that, it helps you to see, because we know muscles can only pull. And we know one of the things about pulling forces like rubber bands is that if you want to stretch it, you have to move it in the opposite direction of their pull. Kind of makes sense. If a rubber band's trying to pull in, if I want to stretch the rubber band, I have to literally lengthen it out. I have to pull it out. So with muscles, if I want to stretch my left lateral pullers, I need to bend my neck to the right to stretch, of which pulls to the left. I'm trying to stretch the muscles on the right side, I need to bend to the left. If I want to stretch the muscles that pull me in a direction flexion, I want to extend the neck. If I need to stretch the extensors, I need to flex the neck. And vice versa with the rotators. So imagine being able to visualize how all the different muscles pull, and then you can reverse engineer what position I need to go in to stretch it. So if I'm trying to stretch my right sternocleidomastoid and I know it's a right lateral and a flexor, I want to extend and I want a left lateral. And then if you know that it's trying to twist you to the left, you want to look back to your right. So just showing you how this stuff can be useful. Probably overwhelming right now if you haven't watched the lecture on it. I promise you, feedback from most students is the cross-sectional visual approach to how muscles pull is very useful. Okay. I'll take a pause right now to see if there are any questions or clarifications. Is this being helpful for you guys? Is it not being helpful? Maybe you can't hear me. I hope that's not the case. So I'll open it up for general questions. I am still, haven't shown any symptoms yet. So if I'm symptom free tomorrow, per my doctor's orders, I will have a class on Friday. Now, that being said, again, if you are vulnerable to illness and you're like, I got 3 words for you, nope, nope, and nope. That's why we do the live stream. So I'll communicate that tomorrow if class will be online, but not online, but streamed, or if I'll be there in person for those of you that want to come in person that learn better that way, or if you just don't feel like it, just watch the stream. So I'll communicate that on tomorrow, on Thursday. Any questions, clarifications? I can't emphasize this enough, guys, on the Moodle PDFs, the things that I emphasize in class, that's the stuff that I'm going to ask on the test. I'm really trying to simplify and emphasize. What do you need it for? Pros and cons, speed, torque. If I get more torque, I'm going to lose some speed. If I gain more speed, I'm going to lose some torque. movement strategy, same way. And if I gain more speed with sequence, it's got to come at a trade-off. It's going to be harder to be accurate. It's not to say you can't be accurate, but imagine, I don't know if you guys have ever heard of a sling. Like, think about like Bible stories, right? David, Goliath, slinging a rock. You can make that rock or that stone go very fast with the sling. It's very far away from your hand, from your axis, and it's light. You can make it go very fast. But releasing it and making it hit a tin can, 20 feet away, 10 feet away, it's hard. Because with the trade-off of speed comes less accuracy. In other words, you have to release, if you're trying to hit a target with that sling, remember that stone is constantly changing direction as it's whipping around. So you have to release it almost perfectly for it to hit its target. And that error is going to be multiplied by distance, meaning if you're a little bit off, as that can goes further and further back, the stone will go further and further miss. It will miss greater and greater. So again, the key things are trade-offs. The trigonometry stuff, I just want you to see angles. And I want you to see that it's not linearly proportional. It's inversely proportional because of the squaring, a squared, b squared, c squared. So when we have muscles that look like they're really steep, they still have a vertical, a horizontal component to pull. When we see a muscle that looks like it's almost all horizontal, there's still a vertical component to pull, and it's more than what our linear thinking brains want to give it credit for. Okay. Any questions, clarifications, comments? I'm going to upload this video to YouTube, just in case if anybody wants to go back and rewatch it. All of your videos for this unit are updated, including the muscles of the cervical. And then on Friday, we'll get into sample questions. But even though some of them we go through in class, we'll give more sample questions. The circles don't tell you who's working. They just tell you how muscles pull. You still need to figure out, hey, an external force is trying to extend me. I learned that I need my flexors. Those are the right and left sternocleidomastoids. Those are the positive working muscles. And so if I see flexion when I'm working those flexors, that's got to be concentric. That's got to be positive work. And if I see extension while I'm working my flexors, that has to be negative work. Flexion pullers allow extension through eccentric. So we'll do some more of those kind of practices on Friday and Monday. All right, guys.
Dr. Campbell?
Yeah, what you got?
Okay, you just said something about the muscles, and I think it was helping me understand something. You were talking about like a triangle with the muscles. Like if we're looking at the gracilis versus like how like the bicep is straight along the bones and joint versus the gracilis, how it goes in at an angle. What's the difference between those two again? Like, is it something to do with like angular and
No, no,
linear?
great. It's just pulleys. It is advantages of pulleys. So for that gracilis, if you look at the PDF of the simple machines, it says basic biomechanics for pulleys and levers.
Mm-hmm.
So if you scroll down and you see that gracilis type muscle, right, coming down, and all of a sudden when it crosses the knee joint, those condyles protrude medially, right?
Mm-hmm.
And so you see that muscle coming down, and all of a sudden it's like turning a curve on the road. So all of a sudden, instead of coming down steep after it's done going through those condyles, now it inserts more shallow. Like in other words, it has much more of a horizontal component of its pull at the tibia, at that pes anserine insertion. Can you see that picture or not now because you have your computer up?
Oh no, I'm looking at it right now.
Okay, great. So all that's saying is that We have different structures. Let me try to summarize it this way. We have different structures that are all giving similar advantages, but the difference in the class is just the structure itself. What is it that's giving the advantage? So you look at the first class, that's a specific type of flat bone called a sesamoid that's housed in the muscle itself.
Hmm.
And then you have the third class, like you're saying with the gracilis, where it's the condyles, the joint, literally the joint itself kind of helps create a better angle of pull. And
Oh,
then for
okay.
the bicep, and then the bicep, you look at it, it's literally another muscle. It's the brachialis muscle that is serving as the leverage of the bicep.
Oh, okay. So, because the brachialis is underneath it,
Yeah, yeah,
it's kind
absolutely.
of like, is it kind
Yes.
of like how the not the same thing, but is it like how the sesamoid allows, I mean, no, the patella allows more leverage for that?
It's the same end result, but what is the means is what makes it different, if that
What do you
makes
mean?
sense, right? So in other words, both the quad and the bicep are going to have better leverage, but one is because of a bone housed in a
Okay,
tendon, and the other is because it's piggybacking on top of another muscle. Like
right, right. That
what
makes sense.
what
I get that.
what it is different, and that's why they have different classifications, but all similar in results, and that's better mechanical pull of a muscle, but through different means.
Okay, that makes sense. I get that. Okay.
Awesome. And I appreciate that question because I don't know what I don't know. So I can't help to clarify unless, I get that kind of feedback. So and those are the only three I'm gonna ask you. The class fours are kind of weird and kind of a hybrid, and the twos are really weird because its example is the eye, but they all kind of similar in that you're taking a muscle that's pulling one way and you're redirecting its pull another way, but what is redirecting it is different. And so
Hmm.
that's how they're getting the different classifications. What is the structure that's redirecting the pull of our muscles pulleys?
Okay. Um, how much of the laws will you be asking on the exam?
Uh, I obviously not half of the test. I might ask which, maybe a couple of questions, but more specifically, like this law of which law was F is equal to ma, which law was inertia, which law was rotational inertia, right?
Okay.
Moment of inertia. Which law was if you push on your desk, the desk pushes back on you. Which law was that?
Mhm.
Does that make sense?
Yes, sir.
So all for checking of understanding, on a general level.
Okay. And one more question.
Yeah, shoot.
With force and moment, when it comes down to linear and angular,
Hmm.
um, is there anything to do with joints and muscles with that, or is that just strictly like knowledge-based physics?
Can you? I missed what you said. Can you repeat that second part, please?
Yeah, is the linear and angular, does it have
Hmm.
anything to do with joint motion and muscle contraction, or is it just simply physics-based
No,
knowledge?
at all. Well, joint motion and muscle contraction is physics based, right? Because
Right.
motion is a kinematic thing, right? My elbow is flexed or my elbow is flexing. The kinetics is, well, what's flexing it? What are the rotational forces? But if you remember, or what I'm trying to emphasize here is that you can't have a moment without a force, but it's just when force is multiplied by perpendicular distance, that's what creates a rotational force. But linear forces are still important in our bodies and our muscles. Remember, for stability, right? Trying to maintain joint stability, there's going to be non-torque linear pulls
Mhm.
that are trying to maintain, like I think in class I gave the example, if you're doing shrugs, right, and you grab some heavy weights, you're going to feel your bicep and your tricep puffing out, even though you're not trying to do any kind of elbow exercise, because those muscles cross the shoulder And when you have a heavy weight, it's literally trying to do this to your socket, right? To your ball and socket. And so
Mhm.
you have to have muscles that are linearly working to try to maintain stability. Um,
Okay. So
uh,
will linear be like your muscles are like kind of equal to the direction of the like your muscles are working to prevent that direction instead of it being rotational and you get what I
well,
mean?
well, well, let's go back to that gracilis question you had on the pulleys, okay?
Hmm.
Right? So so we can look at that where that muscle is inserting, right? On that tibia, on that pes anserine. You could say, well, that muscle is pulling the tibia up and to the right as we're looking at it. Obviously, this would be that person's it's pulling medial. Does that make sense? It's trying to pull up and medial.
Hmm.
Okay. Now the torque or the moment is the X component, this component, part that is positive X, because the angle of inclination of that muscle is in quadrant one. Some of it is positive Y, some of it is positive X, meaning some of it is pulling up, some of it is pulling across. Do you see that?
Yes.
The muscle is pulling here as a resultant. Some of that is here, some of that is there. We're good so far?
Hmm.
Okay. Only the part that's pulling here is actually trying to rotate your hip.
The one on the peasant's ring.
Only the component that is here is actually trying to rotate. Like in other words, if you were doing a manual muscle test for your abductors or adductors, wouldn't you want to push cross,
Right.
right? So what I'm trying to show you is that the rotary components of these muscles are only the component of that resultant pull that's perpendicular to the axis of rotation. The component that's trying to just pull up is literally just trying to take the tibia and push it more into the femur.
Okay. I see.
And again, this is nothing where I'm expecting you guys to master at this level. I'm just introducing you to just because that muscle is pulling on that bone doesn't mean all of that muscle's force is trying to rotate you.
Okay. Mhm. Yeah, see
And
some of this. Oh, go ahead.
no, I was going to say, so the rotational component is just the angle of that muscle that is perpendicular to your tibia. So in other words, um, here is your, let's say this highlighter is your tibia as I'm looking there, and there is the angle of that gracilis. Okay. What I'm trying to show you is only this part is actually trying to rotate your hip.
Is that because that's the um insertion point?
It's
Like,
because that is the only component of that muscle that's perpendicular to the tibia. That's what a torque is.
oh,
Yeah.
okay.
Yeah. Yeah. The vertical part isn't trying to rotate your hip. The vertical part is just trying to draw your femur into your socket or draw your tibia
Right.
into your femur. Only the part that's perpendicular can actually try to spin you.
Right. So that'd be the rotational.
Yes, yes.
Okay.
So the linear stuff is still important. The linear stuff is trying to keep tibia on femur and trying to keep femur on acetabulum, right? And that's why
Hmm.
you have a lot of hip muscles, big, powerful hip muscles that aren't just there to rotate your joint, but are there to make sure you don't have a bad day. This, this,
Okay.
you know, that's a bad day. So the linear stuff is for the stability purposes, and the perpendicular components are for the rotational purposes. And that's all I'm trying to get you guys to see, that when you have muscles that are pulling at angles, only the pull that's perpendicular to the long bone can actually try to rotate you. And the part that's parallel with the long bone is trying to stabilize you.
Okay, stabilize. If they're parallel, they stabilize. If they're
Yep,
perpendicular, they
yep,
rotate.
absolutely. And I have examples in some of the other PDFs of, muscles pulling at angles, and notice how this is, and it's not that the linear still has moment, but the moment is zero because there's no perpendicular distance. So it could be 1,000,000 pounds. If I apply 1,000,000 pounds into the merry-go-round, if I 1,000,000 pounds is probably too much. But if I apply a huge force right here, I'm not going to try to spin the merry-go-round. I'm trying to just
Right,
shift the merry-go-round. That's what I'm
right.
trying to get at. So so we have muscles that contribute at angles, and the part that's into the axis has no moment because there's zero perpendicular distance. So it doesn't matter the force. If the perpendicular distance is zero, it's not trying to spin you.
So
And
on
the
the,
component, go ahead.
I say, so on the exam, could I expect you to specify if the force is perpendicular or
Oh,
if it's
absolutely.
linear?
Yeah, let's
Okay.
go. Let's look at our Moodle, and let's see, go to basic trig,
Mm-hmm.
and I have some examples. So like on the third page, maybe, yeah, page number 4, when I talk about collinear and concurrent, and I give several examples of, hey, look at that muscle F. So you have a muscle that's pulling on a bone, but not all of that resultant is actually trying to rotate your joint. Only the force that's perpendicular to that long bone is actually trying to spin. The force that's parallel is trying to stabilize. And then if you go down to the next slide, I give another example of stabilizing versus rotary in a resultant muscle pull. And then on the next one, I give even another example. So I try to give several examples of how muscles pull on bones, but they pull at angles, and only the component of that muscle that's perpendicular to the bone is actually trying to rotate. And I think in class I use like the door example, how like if I give a 200-pound force, but it's parallel to the door, I'm not trying to open or close the door. Like my force has to be perpendicular to the hinge in order to try to make the door open or close.
So like on page 5 with the bicep right here,
Mm-hmm.
um, it says the rotary force that's perpendicular to the bone. So
Mm-hmm.
if you were to have that on an exam, how would you like formulate
I
your
would
question?
I would probably try to phrase as many questions as straight off of examples that we've done in class. Um, with this muscle is pulling up and to the left. In basic trig, we say positive y, negative x. True. I'm
True.
using the example. What's that? You
I
can be
said
honest,
true. Oh,
but
I was
do you
just
understand what
laughing.
I'm saying? That's
Yeah, I think so.
okay. Well, let me try it again. That muscle, as we're looking at it, is pulling on the lower arm, right?
Mm-hmm.
Okay. It's trying to pull the lower arm up, and it's also trying to pull the lower arm to your left. True? Now it's doing it because it's pulling at an angle, but
Okay.
some of that resultant is positive y, and some of that resultant is negative x.
Okay.
Now remember, this is just a static picture where he's just holding this position. So there's no movement. It's just that's how the muscle is pulling. It's pulling in this direction. And some of that pull is here and some of that pull is there.
Can can
And then
any
if
muscle
you see that, then I could take the next step. But do you see that part?
of the perpendicular and
That the muscle is pulling as at a resultant, and
Uh-huh.
one of the components is positive y, and another component is negative x. It's pulling up and across. That's like saying if you're walking northwest, some of your distance is north, some of your distance is west.
Oh, okay.
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 So what I'm trying to show you is that if you're trying to walk as far north as possible, any distance you travel west isn't going to count. So it's similar. That muscle has two different, that's what concurrency means. That muscle has two different functions happening at the same exact place. That muscle is the northern part of that muscle's pull, for this example, is actually trying to rotate you. It's trying to create flexion moment. It's being a flexor.
Hmm.
But the west component is being a stabilizer. It's trying to keep pulling up onto the humerus.
Oh, okay. See that? There you go.
All good. I know it's weird, right? It's just something we
Yeah.
don't really talk about a lot. But I'm just trying to show you that muscles aren't just doing work because of motion. They do a
Hmm.
lot of work for stability to make sure that while you're doing these exercises, this bone doesn't come out of socket from the other bone.
Right. So
And
can any, I'm
go
sorry,
ahead.
go ahead.
No,
Okay.
no, please.
Can any muscle be a stabilizer like in linear? And but can any muscle be in perpendicular moment?
Well, there's trade-offs. There's trade-offs. So remember, every force is linear. It's just when you have a force multiplied by a perpendicular distance, that's when things become rotational. In
Hmm.
class, I use this analogy. I said in athletic training, and not just athletic training, it's just we see it in athletic training because we're on the field, but you'll have certain joint positions where joints are more vulnerable to being dislocated. And one of the reasons is because at certain angles, you lose some of the stability component of that muscle's pull. So in other words, if my elbow was maybe more an anatomical, the poles are much more stability than they are rotary. That's why, like when you're doing curls, like it gets harder and harder when you go out here because the muscles are losing perpendicular pull and trading off for more stability pull. So when you're like at certain angles and you gain more rotary component, you lose certain stability components. That's why like elbows might dislocate when you're flexed and you land on the ground because
Okay.
because the muscles rotary is in the same direction as stability. And so all of a sudden you have this shift and there's really no muscles there to kind of try to stop that kind of stuff when you're so there are trade-offs in these angles. And that's actually why at certain angles, joints are more vulnerable to dislocations because you gain some rotary at the detriment of some stability.
Okay. That makes sense.
But I'm not going to ask that on the test, but that's where this stuff can start to be applied. That we traditionally only look at muscles for their rotary components, but it's very important, especially in allied health, for us to see muscles for their stability components.
Hmm.
And and that's when you'll hear a lot of like things of co-contractions where you have flexors working with extensors, but it's not the rotary component that's working together. Those are actually antagonistic. It's sometimes you'll have co-contraction and the opposite, the antagonists are actually working a little bit for stability, like to just try to maintain joint stability, even though the agonist, like in other words, if I'm doing curls, I might get some electromyography of my tricep, but it's not that my tricep is helping me on the curls. It's my tricep is working to try to keep my elbow and my shoulder from not dislocating.
Right. Okay. That makes sense. Well, Dr. Campbell, I appreciate your
Oh, you're
time
welcome. I hope that
and
was helpful, and hopefully we'll see you guys on Friday. Okay.
hopefully you have a great day.
All right. You as well. Be well.
Bye bye.